A car speeding down a road and a circular ripple expanding in a pond appear to be separate physical events. Despite these differences, both scenarios are governed by the exact same mathematical engine, the instantaneous rate of change. We can see this in how we calculate speed. This equation shows a car's position, s, as t cubed. To find its instantaneous speed at any moment, we take the first derivative, which gives us the velocity equation, v equals 3t squared. We have a formula for how fast the car is moving through space. But when a driver steps on the gas, the speed itself changes. To track that specific change, we need to look one level deeper. This is acceleration. On a car dashboard, your speedometer tells you how fast you are traveling. This second gauge tracks how quickly that speedometer needle is moving. It is the rate at which speed itself is changing. To find the formula for acceleration, we take our speed equation, 3t squared, and apply a limit over a tiny time interval, h. We expand the binomial, 3 times t plus h squared. After multiplying terms and canceling h, we are left with a new derivative, a equals 6t. At 4 seconds, we plug 4 into our time variable, resulting in 24 feet per second squared. This means that at that specific moment, the car's speed is increasing by 24 feet per second every second. Taking a derivative of a derivative allows us to map exactly how that velocity gains momentum. Apply this logic to the pond ripple. Here is the expanding circle, with radius r and area a. Instead of time, we ask a geometric question. If the radius increases slightly, how much new area is created? This relationship is a equals pi r squared. Using the same limit process we used for the car's speed, try to find the derivative of this area formula. We are looking for the rate of change of area with respect to the radius. The algebra follows the same pattern. We expand pi times r plus h squared, subtract the original area, and divide by the change in radius. As h reaches 0, we find the derivative, 2 pi r. This demonstrates that derivatives map to spatial dimensions just as precisely as they map to time. In a real pond, the ripple is dynamic. The radius itself is expanding as the seconds pass. We have a chain of dependencies. The total area depends on the radius, and that radius depends on the passage of time. To find how much total area the ripple gains every second, we link the geometric derivative, how area responds to the radius, with the physical speed of the radius expanding over time. This is the chain rule. We take the change in area over radius, dA dr, and multiply it by the change in radius over time, dr dt. The dr terms cancel out, leaving us with the rate of area change over time, dA dt. If the radius is 3 feet, its geometric rate of change is 6 pi. If the radius grows at 2 feet per second, we multiply those rates to get 12 pi. At that exact moment, the ripple is adding 12 pi square feet of area every second. Multiplying these independent rates provides a precise measurement for multi-layered physical systems. Today, we followed 2 parallel paths. In path A, we moved from a car's position to its speed, and finally, its acceleration. In path B, we tracked how a circle's radius dictates its total area. The core concept remains the same regardless of the variables. A derivative tells you exactly how quickly one property changes the moment you alter a connected property.